Yeah, hello and welcome back our class of foundation engineering. Today we are going to talk still on chapter number 1. We are going to talk about numerical method used in modeling of earthen structures. So this part number 8 of this chapter, we will do 2 video on this part. Okay, so this first video will be kind of introduction. Okay, and we will do another video still about this numerical method, these numerical methods used in foundation engineering. Okay, so we will talk first about finite different approach or finite different method used in geotechnical engineering. So geotechnical engineering problems involve some equations with temporal or spatial variable. Temporal means like time, and spatial means space. Okay, so dynamic loading situation depend on both time and space. It means the loading will will change according to both time and space. Okay, and static static load static loading rely only on spatial variable. That means, for example, if you load a pile during pile loading test, the load is constant in time. Okay, however, there will be displacement, for example, downward. Okay, so it means in time this load is constant until the test finish. However, in space, for example, if you do it in a z direction, for example, let's consider that, you will see that the load is, there is displacement, the load is changing in the space. This is I'm talking about constant load. Okay, constant load. I'm not talking about when the load is increasing, for example. So some people also don't know what is difference between static load and uh, dynamic load. Let's consider this. I was saying just now that I am talking about constant load, not uh, load that is changing, increasing load. Okay, so let's suppose that this weight, when you hold it, just one hand, and you keep it like this. This means, for example, static load. So if you load pile, static load, pile loading, I think previously I have shown some example where people use, for example, fill bag of sand and put on the pile, for example. Okay. So this is illustration. However, if you do this movement, you do something like this, up and down. This is, for example, can be considered as like dynamic load. Okay. Another example is this one. Supposing this car is standing. Now, this load, the load of the car is kind of static load. It can be considered as this load, this line. Okay. During the time, in the time, the load is not changing. You see, about average, this line. However, when the car is moving, the load is, the curve of variation of the load is like this in the time. This is time load. So this is just illustration to show you the difference between static load and dynamic load. For example, a train that is moving on railway, you have to consider static load during the design of railway, or if bridge, cars or train passing on the bridge, you have to consider dynamic load, okay? Conventional mathematics solutions are feasible for simple geometry and loading condition. So we can if the geometry and load condition are very simple, we can use just conventional mathematical solution. Sometimes we can solve them analytically by ourselves without using any machine or something, okay? Can use it using, for example, constant of integration determined by both methods. So dynamic and transient loading situation with known initial deformation of geotechnical structure, for example. This is one case. This category of problem is known as initial value problem, okay? So if you have this kind of problem, you can use just conventional mathematical solution for that. Dynamic and transient loading situation with initial deformation of geotechnical structure. Number two, static load. This is dynamic. Number two is static load. Static loading condition with fixed boundary loading and deformation condition. This category of problem is referred as boundary value problem. Okay. Sometimes we have complex loading condition. So this kind of condition combine initial and boundary value problem. Do you remember the initial one is when you have dynamic loading, and boundary one is when you have a static loading condition, okay? For intricate geometry and loading, deriving explicit solution to differential equation is impractical. So it means when you have complicated loading and geometry situation, you cannot, it's difficult to derive good solution, reliable solution using simple mathematical equations, okay? Numerical solution techniques offer viable alternative. In that case, when the geometry and the loading condition are complex, using numerical solution is better, okay? By replacing derivative with numerical difference forms at predefined interval by interval, forming finite different mesh or finite different method or finite different approach. Okay, this is the title of this part. Okay, so all is to say that if you have simple geometry and loading condition, you can use just analytically mathematical equation, simple mathematical equation to solve your problem. However, when the geometry is complex and loading is complex, doing it with simple mathematical equation is almost impossible. You have to use some numerical solution techniques. Okay, so here we are talking about finite different mesh. This is how it works. This is just illustration, okay? So you have your geometry, for example, original 3D geometry. Then you divide it by small pieces, small predefined interval. You see predefined interval here. So that is forming a finite different mesh. And you can even make it like this. This is coarse mesh. That one is element geometry form for the coarse mesh. Okay. As you can imagine, you can do this in a computer also, but the secret is just dividing the whole model, the whole geometry in small pieces, and then you study each of them, each pieces. Okay. So the solutions accuracy depend on the mesh fineness. Do you understand? The more you divide this element, small they are, the more you have accurate solution. This means if you need better solution, you have to divide your geometry in finer element and study each of them. It will take time, more time. Okay. Advancement in computing enable refined solution. So finite different techniques are particularly useful for non-homogeneous loading and geometrical condition. This is just to say that this kind of techniques are used when the geometry and the loading are complex. Okay. So many finite different solutions will be illustrated in this program, this foundation engineering course, for the following problems. For example, we will in chapter, I don't know exactly, I don't remember, chapter 5, or we will talk about footings on elastic foundation. Okay, something like that. This is just illustration, please. So we will use finite different approach to solve this kind of problem later in this program. So just keep following. And we will also use finite different approach to solve problem related to pile driving analysis. Pile driving, if you drive pile, this in illustration, so you have the ground around the pile here, and by using this hammer, this kind of hammer to impact, to hit the pile so that it can go in the ground. Okay. We can model this like springs. Can you see spring between the pile material, and also the spring can be used to model the soil around the pile. So anyway, we can use later find a different approach, an example to solve this kind of problem as well. Okay. The last one, two-dimensional seepage analysis. If you have a dam or dike or any embankment that is near water, retaining water, okay, you may have seepage. So we will use later one example using finite different approach to solve this kind of two-dimensional seepage analysis. Okay. Okay, let's now talk about finite element approach. Previously, we talked about finite difference approach. Now, finite element approach. It is not same. It is not the same thing. Okay. Here is different, just illustration, difference between finite different approach and finite element approach. Okay. If I take this, for example, my geometry, and I divide it in small element. This is for finite element method, FEA, and this one, finite different method, FDM. FEM, FDM. Okay, so in this case, as you can see, we have, this is what we are calling mesh element, and each element has, for example, here, 4 node. It's not always 4 node. You have sometimes instead of square or 4 sides, you have sometimes triangle, 3 sides for each element. So anyway, for each element, you will have several nodes. For example, here, this element, we have 4 nodes. 1, 2, 3, 4. Okay. However, in case, as you can see, name here, node, element node. Okay. And domain boundary, the limit of the domain boundary. Okay. So in case of finite different method, the element is not represented by several nodes. Each element has one node, the cell center here. We're calling it cell center. Okay. Cell center. This figure is not summarizing all the difference between FEM and FDM. However, it can show you like roughly what can be the difference between these two methods. Okay, as you can see, this one FEM is more complicated, if you can say that, and you need to consider more things in FEM. Okay, so if we check this table, we can see FEM is more accurate, and but it is more complicated also, more exigent on the mesh quality. Okay, and it requires more computation power. Okay. On the other hand, if you check for finite difference method, you will see that it's the older one, of course, but it's faster because it's easier to calculate. It is the easiest one. However, the accuracy is not uh, that high when it is compared to the FEM. Okay, as you can see here, only one cell center for each element. Okay, however, here each element 4 nodes. So it means the latest generation is this one, FEA method, and this is what many software are using, FEM. Okay, so there are a lot of software using this. I guess you know already. So the finite element method, this one, FEM, model load deformation. It allow to model load deformation in structure like foundation engineering, pile, retaining wall, facilitating essential design study. Let's take this for example. This is one illustration example. We have this building, high-rise building with a lot of stories. If you want, you can count them. If you want to know how the whole structure, this whole building, will affect the ground, the foundation, you can see here, you can make a model with FEM to show you how the ground will deform, where in the ground the stress will be high if this loading condition and this ground condition are considered. Okay, if we consider this is example of retaining wall. Okay, we have the retaining wall here in blue color, and this is the soil foundation. Backfill is here, and interface between the structure, the retaining wall, and the soil. Okay, another one is here, for example, same retaining wall, but this is, for example, a road, a bridge, or interchange. Do you know this kind of structure? This kind of structure. This is inside is soil. If you see this kind of thing, and I think I have presented once the method how this is built. Okay. In French, for example, they call it reinforced soil. Okay, if I translate it. literally. So you can even try to model this. You see exactly how it is about. And here, the road, cars are passing near this. And you can see how the cars will, it will be dynamic load, how they will affect the structure, okay? And if the structure is stable, this is result, exactly. So each of these elements, as you can see, okay, there is like a rope that is going in the soil, okay? That rope is maintaining this structure. So anyway, any geotechnical or engineering structure can be modeled in using the finite element method, and it can allow you to see the interaction between the soil and the structure. That is the most important thing. Okay, so advanced computational facility enable finite element analysis to establish tailored design criteria through parametric study, considering relevant design parameter for each cases. Okay. Design parameter, for example, if we consider this case, what are the design parameters that can be considered in this case? Okay, you have to consider the soil parameters. Okay, Young modulus, unit weight, cohesion, frictional angle, internal frictional angle. Of course, the weight of the building and the different load, static and dynamic load, everything. Okay, and dimensions. If there is any neighboring building or structures, okay, the rigidity of this wall. So each case has different relevant design parameters to be considered. So it is this kind of FEM is particularly attractive for situation involving design of irregular and relatively complex structure, elephant structure. Okay, when the structure and the loading, the geometry and loading are very complex, finite element approach give us a opportunity to explore, to obtain good solutions. Okay, so in very big project, this finite element method are used. However, you have to sometime determine which software is best for your problem. Okay, there are a lot of software, and these software are sometimes accurate for this type of structure or this type of situation. Okay, so this the basic philosophy for modeling the structure with finite element method is summarized by fundamental principle forming the framework of the FEM formulation. First, make sure the force equilibrium within each finite soil or structure element. This is how it works, the philosophy, how the finite element method works, how it works. Okay. Number two, make sure that deformation, compatibility, and nodal point, I told you, if you take, for example, here we have several nodes for each element. So this nodal point of each finite element, it has to be compatible. the deformation should be compatible. So this is the color code here. Maybe the red color means a high deformation. Okay, and blue means maybe less deformation. So each node is related. The deformation should be compatible at each nodal point of each element. Okay, so the next video we will see the different equations that are governing this finite element method. The number 3 is incorporate an appropriate stress strain behavior model for each soil or structure material in the structure. Okay, relationship between the stress and strain, or let's say load deformation. Okay, load will cause the stress and deformation will result in strain. What is the relationship between stress and strain? This relationship should be appropriate one, very appropriate. So these are the 3 points how finite element approach is working. Okay, so mathematical techniques used to achieve this above tasks, the three method, the 3 point of the philosophy of FEAM. These mathematical techniques will be discussed later. As I said, the next video will be about the mathematical techniques, the equation. Okay, so finite element solution also suffer from all drawback characteristic of numerical approximations. So based on the discussion we had now, what precedes, we can realize that 2 most important steps are need at 2 most important step needs attention for analysis. Okay, and these steps are as follow. There is a mistake here, like grammatical, but I think you can deal with it, you know this. Okay, number 1 is discretizing the soil and structure influence zone. You have to divide it in elements, small elements. Okay, that will allow capturing all load, deformation, geometric, and boundary effect that dictate the overall behavior of your structure under specific loading condition. Okay, divide it as small as possible, mainly where you are expecting more stress, more deformation. Be sure to divide that zone in small element. Okay, this is the first most important thing. Number 2, select the most appropriate constitutive model. I'm not sure you understand what is the meaning of constitutive model, but we will talk about this maybe later, not the next video, but maybe the video after that. Constitutive model, for example, if I say more Coulomb model, this one is constitutive model, Camp-Clay model. So there are a lot of constitutive model. If you take your software, there are some software have several constitutive model. So you have to choose the one that is better, the one that is appropriate for your situation, for your problem. Okay. So that will give you, it will the most appropriate constitutive model will describe as accurately as possible the stress-strain behavior, okay, of different soil and structure material that makes the hyphen structure being analyzed. That is, these 2 points are very, very important. Discretize your problem in small elements, and then choose the most appropriate constitutive model to analyze this problem. Okay, so I think we will stop here for this video. Thank you very much and see you next time.